IP. And so he will give a talk on K-theoretical DT PT vertex correspondence. Please, and please move my picture somewhere. Okay.
Okay, so first of all, thanks for the invitation. I'm very happy to be here in spite of the significant time difference. Thanks for accommodating for that. So I want to report on a recent project, which is joint with Nick Kuhn and Felix Thimm, who are both at Oslo right now, on the equivariant K-theoretic DT-PT vertex correspondence. So I think I'll just jump straight into it. So the underlying setting is we want to fix a smooth quasi-projective threefold over C. And we want to think about ideal sheaves of curves on this threefold. This is the moduli space for what's called Donaldson-Thomas theory. And ideal sheaves of curves fit inside a short exact sequence like this, where Z is the curve. And basically for the rest of today, we'll think only about the case when the threefold is actually toric. And when it is toric, we can restrict our attention to a C3 chart. And in that case, the short exact sequence becomes something more manageable. You're really thinking about certain submodules of C, X, Y, Z. And actually, we'll focus attention on the quotient object, which has a very pictorial representation. You can really just draw each of the weight spaces in X, Y, and Z as a three-dimensional box. And the entire quotient module has a pictorial representation as a so-called three-dimensional partition with legs. So here I've drawn the three possible legs that stretch off to infinity. And in principle, there could be more extra boxes floating around. So roughly speaking, this is what threefold DT theory looks like when your threefold is something toric. Okay. So if we take the set of such 3D partitions with specified legs, so your legs can be specified by their profiles at infinity, which will just be 3 integer partitions, lambda, mu, nu. Then what happens inside Donaldson-Thomas theory is you can form an object called the equivariant DT vertex. And this really arises from geometry, but for now we'll treat it as a combinatorial object. It's some sum over all 3D partitions with these specified legs. It will look like a weighted generating series of such things, where the weight has to do with 3 variables, X, Y, and Z. It really arises from equivariant localization. And for the rest of today, we will work not in cohomology, but actually inside K-theory, which for now just means that the weight changes a little bit. It's some rational function in 3 variables, X, Y, and Z. And there are various limits you can take, which will remove some of this complexity in the equivariant variables X, Y, and Z. For instance, if you take a certain limit and you think about the case where there are no legs, then you're really just enumerating 3D partitions. And there's a very famous formula due to McMahon for this object. So the equivariant DT vertex really is something fairly sophisticated, but in various limits, it will simplify. So on the other side of the stability wall, which we want to consider later on, is this thing called PT theory. And the story for PT theory mirrors the story for DT theory very, very closely. Again, we have a smooth quasi-projective threefold over C.
Sorry, when you say toric, for example, yeah. C3 itself, is it
yes.
allowed? Okay, so then what do you mean on the other side of the wall?
I'll be more specific about this later. Maybe I shouldn't have mentioned the word wall yet. Yeah, so for now, let's just say that this is some other enumerative theory of curves. Okay. Right. So So in PT theory, instead of thinking about ideal sheaves, we think about what's called stable pairs. These are certain two-term complexes of the form OX maps to F, where F is some pure one-dimensional sheaf, and the co-kernel of this map is required to be zero-dimensional. This is some kind of stability condition. And again, if we restrict our attention to some C3 chart, then there's some very pictorial representation of what these things look like. You can draw the minimal legs which are present in F. And as you add in extra boxes in Q, they sort of grow in the opposite direction that they used to grow inside DT theory. Okay. And it's not so important specifically what the combinatorics is. I just want to emphasize that there is some complicated combinatorics going on here with what the fixed loci looks like. Okay. And again, you can form the set of all PT configurations with 3 prescribed legs. And again, you can form this thing called the equivariant PT vertex. And again, we'll think about this inside equivariant K-theory. And again, the weights inside this generating function will be some rational functions of x, y, z. And the nice thing about PT theory is that you have, in some sense, fewer configurations for any specified legs, but the configurations form a more complex family. So maybe now you have some positive dimensional families of such configurations. Though at the same time, you have fewer such things, I guess. You have fewer connected components. So for instance, if you have no legs whatsoever, if you have 3 empty legs, then the PT vertex really just is trivial. Okay, so at the very onset of PT theory, P&T made a conjecture that the vertex for DT and the vertex for PT are related by the following form. And this, we'll see, is one of the simplest possible relations you could expect. And even in the original paper, they suggested that this has the form of a wall crossing formula in terms of certain Bridgeland-like stability conditions inside dp co of X.
So I'm afraid that this quoted phrase is incorrect.
Okay.
Yeah, because well, for PT it's a kind of Ronchi structure, so they live in different worlds. Another thing, I believe that Joyce did not consider counting objects in dbx.
Yes, that's right.
He considered only abelian, so then you should take perverse coherent sheaves as a T structure and probably count there, but then you do not have wall crossing at all.
Yes, that's right. Yeah. So I think when they proposed this in the original paper, there were a number of technical issues that prevented the machinery from working literally. The point of what I'm about to explain is that we
I believe actually I recall, excuse me, I interrupt you. I recall that at the time when they just published, submitted their paper, I spoke to Rahul, I think we met at Princeton, and we find out that modulo some technical difficulties, actually wall crossing formulas of Maxim and myself, they indeed imply this general, not just equivariant, but the general DT-PT conjecture. But again, modulo some technical difficulties, namely modulo the existence of the central charge, because at the time people thought about just Bridgeland stability conditions and the T structure, which are coherent sheaves themselves. And here the right T structure is perverse coherent sheaves. So then I believe that maybe it's more I understand that it's just quotation from their paper, but maybe Joyce should be replaced by Maxim and myself. because
Sure.
we really consider counting in DB in derived sense. So okay, but anyway, it's just small remark. Okay, thank you.
Okay, thanks. Oops. Oh, I clicked something bad. Hang on. Let's go back here. Okay. Okay, wonderful. So anyways, this was a quote from the original paper. And as Jan mentioned, perhaps the name Joyce ought to be augmented by more names. Later on, this conjecture was refined into equivariant K-theory by Nekrasov and Okunkov. I'll say a bit more about specifically what this K-theoretic refinement is later. Okay, but the shape of the formula stays exactly the same. And so the point of the project, which I'm about to say something about, is that we prove this in as full of a generality as you could want. So for three arbitrary legs, lambda mu nu, we prove that this K-theoretic DT-PT correspondence holds. And indeed, the main technique that we use is wall crossing. In two different flavors, actually. We have two separate proofs of the same identity. So it's like in some sense 200% true. And
if
our wall
you
crossing
add
technique,
them, if you subtract, it will be 0.
Yeah, hopefully the signs of the two are the same, so that they interfere constructively. Right. So, anyways, the wall crossing techniques we use work equally well inside equivariant cohomology. So it's not really specific to equivariant K-theory. But the statement inside equivariant K-theory is indeed more refined than the analog inside equivariant cohomology, and so we prove it inside K-theory. Okay, so let me say something about what was previously known before our theorem. Previously, people mostly studied the entire partition function, which means that you, instead of restricting to some C3 chart inside X, you think about an entire projective threefold X, and you integrate 1 over it, and you form this entire generating series. And there is a DT-PT correspondence for these as well. And people mostly studied this DT-PT correspondence inside cohomology. And this was known for smooth projective threefolds, which are Calabi-Yau. I think the first proof due to Bridgeland imposed that H1 of OX is 0. Later, the H1 of OX is 0 restriction was removed by 2 papers from Yukinobu Toda. But as in contrast to what was previously known, as a corollary of our main theorem, we obtain the DT-PT correspondence for partition functions for quasi-projective objects, not just smooth projective threefolds. And the reason for that is just because once you prove something for vertices, you can glue vertices all together. You can patch each of the C3 charts inside a quasi-projective toric threefold together. And there's some factorization of the partition function in terms of vertices and edges. And notably, only the vertices will depend on specifically what theory you're taking, whether you take DT or PT. You can arrange for the edges to really just be independent of the theory. So once you prove some DT-PT correspondence for vertices, you get it automatically for partition function. In a slightly different line of approach, you can take what's called the Calabi-Yau limit of these vertices, and that's where you send the product XYZ to 1. This corresponds to thinking about, instead of some full C star 3 acting on C3, you think about the subtorus, which is the Calabi-Yau subtorus. And inside this Calabi-Yau limit, if you recall, earlier I presented the vertex as some weighted generating series, where the weight is the small w superscript k of pi. If you take the Calabi-Yau limit, that weight really just vanishes. and you really get a numerical generating function. And so you're really counting DT configurations versus PT configurations, and you can do some explicit combinatorics. And so in the case of up to 2 non-empty legs, lambda mu nu, there's some transfer matrix argument which you can do. It's super explicit, and that will automatically give you the DT-PT correspondence. But actually, recently, even in the case of 3 arbitrary legs, where you have non-trivial positive dimensional families on the PT side, it turns out you can still do some combinatorics related to tripartite dimer models, which will prove for you some numerical DT-PT vertex correspondence. So anyways, the fully equivariant vertices, which we want to consider today, these are genuinely equivariant objects. You really need equivariance to even write down what they are. And my view is that they're much more sophisticated objects than any of the partition functions, or if you take the Calabi-Yau limit. These are really very, very complicated things. And so starting from now, for the rest of the talk, we'll always imagine that we fix the C3, and on the C3, we have the standard action of the three-dimensional torus. And we'll work equivariantly with respect to it. Okay, so maybe let me pause here and ask if there are any questions about what we want to prove.
When you say, again, let's specify, when you say that you have action of C star cube, it does not preserve the volume form.
It does not preserve the volume form, that's right. So there will be a one-dimensional subtorus which scales the volume form by some weight, and the remaining two-dimensional thing will preserve the volume form. Yeah.
Okay.
Yeah, that's right. Okay.
I should advocate for some of our graduate students. So here the lambda, lambda mu, those are just the integers, right?
These are 3 integer partitions. Yes.
Okay. Yeah. So that when you say the leg, so basically all those 3D partitions just fits into that 3-dimensional cube with a length lambda mu. Am I correct?
No, sorry. So let's go back to the picture. So here in this picture, we have 2 legs heading off to infinity along the x and z directions. So I've truncated the picture, but you're supposed to imagine that these legs really go on infinitely.
Okay.
And so to specify what these legs are, you can just cut a cross section of them. And so for instance, the leg that moves along the x-axis is the integer partition 2, 1, because the first row has 2 boxes and the next row has 1 box. And the integer partition for the leg along z is just the integer partition 1.
Yeah. And
there's an empty leg in the y-axis, so that leg is empty.
Yeah. So the pi in the pi, for example, PT lambda mu nu, is just one of those 3D partitions that fits into that.
Yes, that's right.
Okay, good. Thank you.
Yeah, maybe I have one more question, but maybe it's sort of stupid. So for in cohomological version, you can consider refined invariants in each.
Yes. Yes, that's right.
Can you do similar?
I have no comment on this matter. Sorry.
Okay.
Yeah.
Okay.
I think there's many people out there who are much more qualified to say something about refinements than I am. Yeah. Okay. So for the remaining 40 minutes, I want to somehow sketch the main ideas that go into the proof of the equivariant K-theoretic DT vertex correspondence. So the very first step, this should really be called step 0, is I keep mentioning the words wall crossing. We should first reformulate this equality from earlier of the DT-PT vertices. We should really formulate that as an actual wall crossing problem. So in order to do this, we first have to formulate in terms of geometry, what is the DT and PT vertices? And the way we do that is we fix some ambient geometry x bar. This will be the product of 3 copies of P1. And we fix once and for all the 3 legs that we care about, lambda, mu, and mu. And so the picture you should have in mind is of some cube. And this cube, away from the origin, there's 3 copies of C2 at infinity, one along each of the three axes. And so you're supposed to imagine that inside this box, we fixed the asymptotics of whatever configuration we're thinking of. We fixed the asymptotics at these 3 boundary C2s. And these asymptotics will be lambda, mu, and mu. And then in the interior of the box, some stuff happens. Okay. So we form a certain moduli stack, frac n, which will be a moduli stack of pairs, O of x bar mapping to some sheaf E, such that the restriction of these pairs to the boundary will be the 3 integer partitions, lambda, mu, and mu, viewed as points inside Hilbert scheme of C2. And this moduli stack will have various components indexed by the numerical class of these pairs, which happen to be 1, 0, minus the curve class, minus the Euler characteristic. And the curve class inside H2 will really just be the size of these 3 partitions, size of lambda, size of mu, size of mu. Okay, so there's some sort of ambient boundary stack, some ambient moduli stack of these sorts of pairs which we want to think about. And following some previous work by Toda, there is a certain continuous family of weak stability conditions on this moduli stack. And the family is essentially some one-dimensional family. It has one special point at 0, such that if you take an element of the family on the negative side of 0, then the stable objects will be the pairs such that O surjects onto E. And the behavior will be locally constant up until you hit the wall, at which there are strictly semi-stable objects where this pair O maps to E might split off many summons of the form 0 maps to some 0-dimensional sheaf. Okay. And as you cross this wall, as you move on to the opposite side, now you're in some stable chamber again. And the stable objects in this chamber correspond exactly to PT pairs, where O maps to E. E is pure one-dimensional. Q, the co-kernel of that Q, will be some 0-dimensional sheaf. So that's roughly speaking what this family of stability conditions is. And it's possible to put a symmetric obstruction theory on this entire stack. And the symmetric obstruction theory looks like X of your 2-term complex with itself, twisted down by the boundary at infinity. Such that in the stable chamber on the negative side of 0, you can use this symmetric obstruction theory to form a virtual cycle. If you integrate this virtual cycle, you really get the K-theoretic DT vertex. In the stable chamber on the positive side of 0, if you integrate the virtual cycle, you get the K-theoretic PT vertex. And inside K-theory, you have to be a little careful about what do you mean by virtual cycle. So usually you start from some Baron-Fantecchi obstruction theory and you construct a virtual structure sheaf. But what was taught to us by Pekrasov and Okunkov is that when you work in K-theory, you should actually take this virtual structure sheaf and twist it by half the virtual canonical. And this twist is actually very crucial for us. It's crucial for the DT-PT correspondence to work, and it's also crucial for the proof. Later on, we'll use a trick where it's actually very important that this kind of twist by K1 half happens. Okay, so that's what the hat on O virtual means. And so this is the geometric incarnation of what is the K-theoretic DT and PT vertices. Amongst practitioners of the field, there seems to be a mild misconception that actually the vertices inside DT and PT theory are some purely combinatorially defined objects. I hope that seeing this proposition will slowly dispel that misconception. Okay, so these really are very geometric objects. They really are the integral over some space of some cycle. Okay. So, sorry. So, seeing this proposition, you can imagine what the wall crossing problem looks like. We want to study how these Euler characteristics, how these integrals of O virtual hat change as you vary the stability condition from tau minus across tau naught over to tau plus. Okay, so now, in some sense, we've reformulated the whole DT-PT problem as an actual wall crossing problem. The problem with this wall crossing, as we formulated it, is that it's not a simple wall crossing. And what that means is that at the wall tau naught, a stable object on either side could split into many strictly semi-stable pieces. Right? So it's not the case that it only splits into two pieces; it can split into many pieces. And later on, and for most wall crossing arguments, you want it to split into at most two pieces so that you can apply what's called master space techniques. We'll see what happens later. And so you have to modify the problem somehow so that the wall becomes a simple wall. And the way that seems standard in the whole wall crossing literature to make this modification is that you add additional data to the objects you want to study. Okay, so instead of studying some moduli stack of the pairs I, we'll study a larger moduli stack, which consists of three objects, I, V, and rho, where V will be some type A quiver. Okay, so you start from your object I, and you form from it some vector space using what's called a framing functor. This framing functor is supposed to capture a lot of the data of the original object I. For us, it eats an object I, and it spits out global sections of an appropriately high twist of the sheaf E. And we include an extra factor of some one-dimensional vector space for the reason that we're working with moduli stacks. So this is a small technical point, which is very important, which is that when you think about moduli stacks, you really have to think about all automorphisms of your object. And in particular, there's a C star worth of scaling automorphisms of the OX, which you also want to rigidify.
Before I completely lost, so support of E is a curve. Yeah, it's a pure one-dimensional.
The support of E is a curve. That's right.
All right. So and the behavior at the three C squares is determined of this support is determined by what?
The behavior is fixed by the condition that if you start with the pair OX maps to E and you restrict it to any of the boundaries,
you fix 3 points in the Hilbert scheme.
That's right. That's right. Yeah.
Okay. And so your framing, can it be kind of interpreted? So what does it do with these? What does it do at infinity? Does it do anything?
I think the framing is not so interesting at infinity. It's more interesting inside the cube. It's more interesting away from.
I understand, but I just wondering because I don't see what does it do at infinity. Maybe nothing, or it's a resolution. I don't know actually.
I don't know if there's a really satisfying answer I can give you. I mean, it really just is you take your sheaf E.
Okay, go on. Maybe it's a stupid question. Okay, go on.
Yeah. Yeah. So here I think the choice of framing functor is actually not super important. I think you just have to pick something that works. And what worked for us is we take global sections of an appropriately high twist of E, and then we add an extra factor to rigidify automorphisms of OX. So anyways, the objects in this auxiliary stack, which we want to consider, roughly look like a certain quiver representation for the type A quiver of a certain length, where the node on the very right has to do with the original object that you started with. Later on, so probably I won't be able to get to this. So let me not say too much about this, but it turns out that it's useful to be able to add many copies of L as opposed to just adding one. It has to do with a certain combinatorial trick. But for today, let's skip that. It's not super important. Okay, so if you fix the numerical class of the pairs that you started with, then these auxiliary stacks involve certain choices. And one choice is, how high do you twist your sheet E? You twist it high enough so that it has no higher cohomology. This is some standard thing. You have to pick the length of your quiver, and this length will pick to be whatever size the framing functor is when you apply it to your object I. For the reason that later on, essentially what happens is we want to think about full flags. So we want to think about chains V1, V2 up to Vn of framing dimension 1, 2, n. So we fix the length of the quiver to be exactly whatever size the framing functor is. Right, and the framing dimension vector will take to be a full flag. Okay. So we started from certain two-term complexes I, and now we've moved to an auxiliary category, an auxiliary moduli stack, which consists of framings of these objects by full flags. Okay. And it turns out there are various ways to lift the original family of stability conditions to this auxiliary stack in such a way that the stable objects at least must have all the maps in this quiver being injective maps. And the useful thing about adding this framing by a full flag is that for various very elementary reasons, now you're guaranteed that at any wall where you have strictly semi-stables, you can only strictly semi-stabilize into a sum of at most 2 pieces, as opposed to a sum of arbitrarily many pieces. And that was the main goal of adding the framing data. So now we really have simple walls, which we want to cross one by one. And even more nicely, when you think about the forgetful map, which eats this thing framed by a full flag and just completely forgets about the framing. If all of your maps, row I, are injective maps, then the fibers of this forgetful map really look like full flag varieties. So one way to say this is that the stable locus upstairs looks like a full flag fibration over the stable locus downstairs.
Actually, this is true in some sense just in pure quiver situation, because the space of framed representation of a quiver, it's sort of a bundle with fibers which are flag varieties, not necessarily. Yes. Yeah, but this is
yes.
Okay.
Yeah, that's right. So here I'm making a very specific sort of statement, but it really is an instance of a much more general phenomenon. Yeah, that's right. Okay. And having this kind of relationship between stable loci upstairs and stable loci downstairs, means that there's a very concrete relation between the enumerative invariance of the stable loci upstairs and the enumerative invariance of the stable loci downstairs, which we'll get to soon. Okay, so now we're in the situation where we have an auxiliary stack and some stability conditions on it, and we want to do wall crossing on the auxiliary stack. And the usual geometric argument for wall crossings, so following work of Mochizuki, Thaddeus, Nakajima, Yoshioka, Kiem, Lee, Joyce, there's many, many people who have all contributed to parts of this theory. I'm sure I'm missing a lot of names, and I do apologize. So anyways, the usual argument for wall crossing is that you form what's called a master space, which we'll call boldface M. And this master space will have a C star action. So this is a new C star. It's not a C star that was present in the problem previously. And the fixed loci of the C star action, you want to arrange for it to come in three flavors. Okay. One fixed loci should be the stable locus that you care about on one side of the wall. Another fixed locus should be the stable locus that you care about on the other side of the wall. And you'll see that you're forced to include a third type of fixed locus, which in some sense looks like what happens on the wall. And on the wall, your stable objects will usually split into two pieces. So your class alpha will split into alpha 1 plus alpha 2 for non-trivial alpha 1 and alpha 2. And so you'll get some third, more complicated fixed locus, which has to do with these splittings.
Yeah, in your case, you put an extra effort to have just a simple splitting in
exactly
the sum of two. But yeah, I'm a bit, of course, I mean, I'm not concerned that you didn't mention our names, but the wall crossing formula of Maxim and myself, it kind of takes care about an arbitrary splitting, just unique.
Right.
Yeah, so then I'm just curious if it's kind of, you can avoid this extra work with framing, just using the general wall crossing formula. Again, I'm not sure how nice will it be in when you go to geometry, but at least kind of in categorical terms, it's kind of pretty standard thing. You start with a point in the moduli of stability where you have some control on blah blah blah, and then you cross the wall, and then there is a general formula. I mean, the Joyce formula, if I remember correctly, it's not very convenient. I mean, it's correct, but it's not very convenient for this multiple crossing, because there are many terms which are in fact equal to 0.
Yeah, that's right.
I believe that our formula, in some sense, better, maybe not, since you already got rid of non-simple splitting, then probably that's okay.
Right. I suppose for us, what's important is that we really try to control the wall crossing using purely geometric means. And it's important for us to do so. Otherwise, it's sort of unclear how to arrive at the final answer. It's possible there might be some more categorical approach to this, which avoids more of the geometric considerations which we have. But I guess for the purpose of this talk, I really want to use some kind of master space approach. And for a master space argument, it's important that you have a simple wall where the splitting is a splitting into at most two pieces. Okay. Right. So sorry. So after you form this master space, the way that you get a wall crossing formula is as follows. Okay. So you think about the integral over your moduli space of the virtual cycle. Okay. And you write down the virtual localization formula for that integral. And the virtual localization formula inside equivariant K-theory looks exactly like I've written on the screen. It's a sum over fixed C star fixed components of an integral over the fixed components of the virtual cycle on the fixed component, and then there's some localization contribution from the virtual normal bundle. Since we want to think about symmetrized virtual structure sheaves, there's a mild adjustment to this formula where you have to add hats on each of the virtual O's, and you have to twist by det of the virtual normal bundle 1/2. Okay. And so for the sake of cleanliness of notation, we'll absorb that det of the virtual normal bundle into this you just add a hat on top of the exterior algebra function. Okay. And so anyways, so a priori, the right-hand side is some quantity inside the localized equivariant K-theory of a point. And what that means is that you start off with the equivariant K-theory of a point, which is just purely the representation ring of all of your underlying tori. So you have z adjoin x plus minus, y plus minus, z plus minus. You have to formally adjoin some square roots because of the square root of the virtual canonical.
So
and then you do some localization.
Excuse me, T corresponds to three-dimensional torus.
K corresponds to three-dimensional. Well, it corresponds to three-dimensional torus and this extra C star on the master space.
But extra C star is this U.
The extra C star is the U, that's right.
Yeah, okay. So the T from the old and U from, okay.
Yeah. And so when you run equivariant localization, you have to localize your K groups, which means you have to introduce the possibility of certain poles. Oh, I'm sorry, this is a typo, where it says 1 over 1 minus U to the A, T to the omega. T to the omega just means some weight of the original three-dimensional torus. Okay, so it's some sort of monomial in X, Y, and Z. And so a priori, the right-hand side has poles which look like 1 over 1 minus U to some power and some monomial in the original torus. But using properness arguments of the left-hand side, you can show that actually there are just no poles in the variable U. Okay, so each individual term on the right-hand side might have poles in U, but once you add them all up, there's a miraculous pole cancellation, and there's actually no pole in U.
So how this proper, I know that it is a standard trick. Can you sort of recall why properness leads to cancellation?
Sure, yeah. So let's imagine we're in the simpler case where you have no underlying torus. So you started with some proper moduli space M. Okay. Then when you run C star localization, you might have poles in the weight of the C star, but an integral of the Euler characteristic of a coherent sheaf on a proper space is some finite dimensional module. And so in particular, it will be some Laurent polynomial inside your equivariant variables. So it will never have some character, which is something like 1 over 1 minus U, which is an infinite dimensional module. So if the boldface M itself were entirely proper, then the quantity on the left-hand side would just be some Laurent polynomial in U, and so it has no poles in U. That's roughly speaking a very simple case of the argument. Hopefully that helps.
Yeah, thank you.
Yeah, right. And so then once you know that the left-hand side has no poles in U, you can hit the whole expression with some residue map. And you'll take some residues in the variable U. Specifically, there's some specific residue map which is appropriate for equivariant K-theory. I don't want to get bogged down in specifically what it is. But if you hit this whole formula with the K-theoretic residue map, then you get some formula like 0 is equal to some sum of residues. And the sum of residues on the right-hand side has to do with integrals over the stable loci that you cared about. So One piece will be some integral over the stable locus right before the wall. One piece will be some integral over the stable locus right after the wall. And you'll get a third piece, which is a more complicated interaction term. And their sum will be equal to 0. So that's some sort of relation that you get out of this master space argument. And that's where, in some sense, all geometric wall crossings really come from. Okay, so that's the rough idea. But the hard problem in all these sorts of wall crossings is that you have to put some obstruction theory on this master space M such that you can actually compute these residues. So usually these residues are horrible, horrible objects, and they're very hard to compute. And if you look in old works by people like Mochizuki, you'll see some fairly complicated things. And so for us, we're going to really take advantage of the fact that in this world of DT-PT theories, we're in some symmetric and 3 Calabi-Yau category. And we're really going to take advantage of the symmetry to put some obstruction theory on M on the master space, such that these residues are understandable and very, very explicit. They're as simple as you could possibly want. Okay, so now we're going to really dive into the technical heart of all this. So a symmetric obstruction theory, it just means that you have
what space, just to remember, are you talking about M or what?
Well, okay,
obstruction theory on M. Okay, good.
Yeah. So at the end of the day, we want to put some symmetric obstruction theory on the master space, which will induce symmetric obstruction theories on each of its fixed loci.
Okay, and for example, in Nakajima-Yoshioka, it wasn't symmetric. Okay.
For Nakajima-Yoshioka, it was not symmetric. Yeah. So
it's rather Donaldson theory and not Donaldson.
That's right. Okay. That's right. Yeah. So to the best of my knowledge, what I'm about to explain is new. I haven't seen this present anywhere. Right. So first of all, let me say very precisely, what is the symmetric obstruction theory? It's a usual obstruction theory E inside D of Qco, such that if you take the dual of E, it's the same as itself up to some shift by 1, up to some twist by some pure equivariant weight of your torus. Okay, so sometimes people call this equivariantly symmetric. I'll just drop the word equivariantly. Okay.
Should I think about K as a line bundle?
Yeah, the small kappa you should think of in our setting. It's the weight of the canonical bundle. It's the equivariant weight of the canonical.
Okay.
Yeah. So to be very explicit, right? We on the space X bar, on the original moduli stack that we cared about, on the ambient moduli stack, which has the DT and PT loci, the obstruction theory looks like X of I with I itself, with a small twist by D. And Serre duality is the following statement on the screen right now. The minus sign corresponds to a shift by 1. And you can rearrange, keeping in mind that if you work equivariantly, the canonical on X bar is kappa, so XYZ, times O of minus 2D. So you really have to be careful throughout the story to keep track of equivariance. So for us, kappa really just is XYZ. And the advantage of working with a symmetric obstruction theory is that if you restrict it to any semi-stable locus where there are no strictly semi-stables, so where the only semi-stable objects are stable, then actually the symmetry will automatically force the restriction of the obstruction theory to be a perfect obstruction theory, which just means that things like things will vanish starting in degree, say, -2 or something like that. So if on the entire stack you have some symmetric obstruction theory, you no longer have to worry about is it perfect or not when you restrict to stable loci. So that's some small advantage. Okay. And so the key observation that we'll make which will help with the residues on the master space, is that if you have a symmetric obstruction theory, sometimes it happens that the virtual normal bundle has a very specific form. The virtual normal bundle looks like a sheaf F minus the dual of the same sheaf, twisted by some inverse power of K. Okay. And when the virtual normal bundle has this form, and you ask what is its contribution to equivariant localization, the contribution has a very nice form. It's a product over the K-theoretic Chern roots of F of rational functions of this specific form. Okay. And rational functions of this very specific form are special because if you take any limit whatsoever in variables that appear inside your Chern roots, all these limits exist. So in particular, you can imagine that these K-theoretic Chern roots, small w, they have some powers of u inside them. And you can ask, what happens when you take the limit as u goes to 0 or u goes to infinity, something like that. And all of these limits will exist. And in fact, you can explicitly say what all these limits are. They'll really just be some sort of monomial in the variable kappa. Okay. And it turns out that the action of the K-theoretic residue map, what it's really doing is that it's just taking certain limits in u. So one limit it will take is u goes to 0, and another limit it will take is u goes to infinity. And essentially, the K-theoretic residue map is the sum of these two limits. And since we have very specific kinds of fractions, we can really just explicitly compute what these limits are. And they look like quantum integers. And specifically, what quantum integer has to do with how many parts of your sheaf F are attracting with respect to u, and how many parts of your sheaf F are repelling with respect to the action of u. So it's some form of index for each C star fixed component. So anyways, the point is that if you use a symmetric obstruction theory and you run equivariant localization, the residues are very easy to compute. Okay. And so what is our underlying situation? Our underlying situation is that we have the original moduli stack, frac n, which has a symmetric obstruction theory. And we'd like to lift this symmetric obstruction theory to the framed stack and also onto the master space. Okay, so the arrow from the master space to the frame stack is in quotes because there's no actual morphism. That arrow is there to remind you that the fixed loci of the master space are related to these auxiliary stacks in some way. Okay. So the technical heart of our work is some procedure where if you have a morphism of Artin stacks, a smooth morphism of Artin stacks, then there's some way to pull back an obstruction, a symmetric obstruction theory along the smooth morphism, such that the resulting pullback is still a symmetric obstruction theory. Okay, this is really the new technical ingredient of our work. Okay, so and we're able to accomplish this in a very abstract setting. So where you really just start off with two arbitrary Artin stacks with a smooth morphism between them, and on the target of your smooth morphism, you have a symmetric obstruction theory. And so I want to roughly outline the idea behind how the construction works, because I think psychologically it's not so complicated. So you really just try to do the naive thing, and then when it fails, you try to patch it off. So the really naive thing to do is you start from your morphism F, and you write down the exact triangle of your cotangent complexes, and above one of the terms sits the original symmetric obstruction theory that you started with. And so let's assume for now that somehow you can lift the map of cotangent complexes to some map small delta like this, Okay, so it's not clear exactly how you find this map, but let's assume this map exists. Then the usual axiom of triangulated categories means you can take a cone. And this cone you can check via long exact sequence. This cone will be some obstruction theory for the source stack. But of course, it will not be symmetric for the reason that you started with some symmetric obstruction theory, which involved things of maybe degree -2, degree -1, degree 0, and degree 1. And then the morphism F is smooth. So the cotangent complex of F sits in degree 0 and 1. And so anyways, once you take this cone, you've modified the original symmetric obstruction theory by adding in some extra stuff in degree 0 and 1. And that really destroys the symmetry, because ideally you'd like to add in the dual of whatever you added in degrees -2 and -1. So so far there's nothing really new. So far this whole thing which I've written has been known for many, many years. And what's new for us is now we're going to try to take this cone of delta and we're going to add in the dual of the cotangent complex of F with some appropriate shift. And the way we do that is we just write down the exact same morphism of exact triangles, except we take the dual of the whole picture. So now we take the dual of the map delta, and we assume that for whatever reason, the composition of delta dual with delta is 0. Okay, so again, it's not so clear why this is the case, but let's assume this is the case. In which case, you can again form a morphism of exact triangles, and you can take the co-cone of each of the columns. And once you take this co-cone, there's some octahedral axiom nonsense, which will also form an exact triangle in the very top row. So now you have some 3×3 square. And the co-cone of this map psi is, I claim, the symmetric obstruction theory that you wanted on X, for the reason that you've made some modification by the cotangent complex of F, and you've made the dual modification by the dual of the cotangent complex of F with some appropriate shift. And so you have some hope of seeing some symmetric obstruction theory. The problem with this naive attempt is that we made a lot of assumptions, right? We assumed that there exists some lift, small delta. We assumed that for whatever reason, the composition of delta dual with itself is 0. And for various technical reasons, which involve the non-factoriality of cones inside dbCo, you also have to check that this map zeta in the upper left, which you obtain from the octahedral axiom, you have to check that it really is the dual of this map psi on the bottom right. Okay, but so there's a whole bunch of technical conditions. If they're all satisfied, then actually this 3×3 square is symmetric across the diagonal, and the original symmetry of the obstruction theory on the target will be inherited by this E of X, which will become a symmetric obstruction theory on the source. Unfortunately, none of these assumptions hold in general, but you can check for stupid reasons that they hold if you're on some affine chart. And so the main insight that we had was, okay, then we can run this whole story, it's all locally on an affine chart. And there's this notion due to Kiem and Savvas of what's called an almost perfect obstruction theory. And the idea is that you fix a metal atlas on your stack, and by various strong theorems due to Alper, Hall, and Reed, you can actually assume that the atoll charts in this atlas are affine, and they're preserved by the T action. And what's an almost perfect obstruction theory? It's on each of these atoll affine charts, you have a perfect obstruction theory. And the perfect obstruction theories, maybe they don't glue, but the obstruction sheaves for the perfect obstruction theories, they glue to form some global object on the entire stack. Okay. And it turns out that that's enough to form a virtual structure sheaf. So the key idea of Kiem and Savvas is that you don't need some global perfect obstruction theory. It's enough to have local perfect obstruction theories that tall locally, such that they glue to form a global obstruction sheaf. Okay. And so in our setting, what can we do? We can return to our smooth morphism of Barton stacks, and we can think about the stable locus on the source. Okay. And we can choose some Étale atlas, and we can run our symmetrized pullback construction in the naive way on every Étale affine chart. And we can check that the resulting symmetrized pullback obstruction theory really forms an almost perfect obstruction theory. That these local symmetric obstruction theories, they glue in the sense that their obstruction sheaves glue. And we can also check that the resulting virtual structure sheaf satisfies equivariant equalization. Okay, so that's really the heart of our whole thing. I'm running out of time, so let me just skip over a lot of the rest of the story. But roughly, the only thing that really remains is to put all this back together, right? So now you have some master space, you have some obstruction theory on it. We'll use master space techniques to do wall crossing on the auxiliary stack. The auxiliary stack is related to the original DT and PT vertices by some factor, and the factor really is some quantum integer. The quantum integer arises because we have this equivariantly symmetric obstruction theory. So having this equivariant weights kappa is equal to xyz means that a lot of integers that you used to see in these wall crossing stories are now quantized into quantum integers. And the geometric meaning of these quantum integers is that when you integrate along things like a Pn fibration of an appropriately symmetric thing, then you see these quantum integers arising. Similarly, if you integrate along full flag varieties, you get some factorial of these quantum integers. And this quantizes a lot of formulas inside Joyce-style. So we actually have two separate ways to do the master space. One follows work of Mochizuki, one follows this universal wall crossing work of Joyce. They're slightly different. They produce slightly different formulas. But the simple wall crossing formulas roughly look like this. So it's the invariant you cared about on one side of the wall minus the invariant you cared about on the other side of the wall, plus some sum over all possible splittings. And what happens is that the counts of the curves that you cared about will split off zero-dimensional sheaves. And so you have framed invariants of zero-dimensional sheaves which appear. You have splittings of a full flag into two full flags. And there are some conditions on what the splitting of the full flags has to look like. And then there's some certain combinatorial term that has to do with the splitting. Okay, it has to do with some combinatorial data. And then you can recurse to get some full wall crossing formula as you cross the simple walls one by one. Okay. So there's some combinatorics that happens. In the Mochizuki-style setup for our master spaces, you get some giant formula in the end, which you can really just explicitly simplify. There's some combinatorics that has to do with splittings of full flags. And you can prove some combinatorial identity, which roughly looks like this. We haven't seen such combinatorial identities in the Q combinatoric literature yet, so these might be new. And on the other hand, if you set up a Joyce-style master space, it's a slightly less ad hoc construction, but it's harder to solve the combinatorics, and we have to use a trick. Yeah. So, anyways, let me skip past a lot of these details, and if it's okay, let me take one more minute and say something about possible future applications. So, I think Sorry, what?
Yeah, go ahead. Yeah.
Okay, yeah. Sorry for going over time. It's sort of interesting that most of the ideas which I've tried to outline today didn't really depend on the fact that we're trying to wall cross from DT to PT. I mean, we really just used that we had some ambient moduli stack to start with, and we wanted to cross from one stable locus to another. And there were mild assumptions on the initial setting, but we didn't really specifically use that it was threefold DT and threefold PT. So equally well, I believe that the machinery we have can be applied to things like there's a fourfold DT-PT correspondence. That's the most obvious thing to apply it to. The only problem here is I have no idea how to do symmetrized pullback, for the reason that when you work on fourfolds, the construction of a virtual cycle is much more subtle. So you can't do the usual Bayer and Pantecchi thing. You have to do this newer thing due to O and Thomas and what they do really crucially uses that the moduli stack of sheaves on this fourfold has some -2 shifted symplectic structure, and they really have to carry around this -2 shifted symplectic structure. And I don't know how to preserve it as you do this whole symmetrized pullback process. But assuming that all the technicalities work out, our machinery should equally well be able to prove the fourfold DT-PT correspondence. There are also various other stability conditions, which are not the DT and PT stability condition. So for instance, if you have some crepant resolution of a threefold singularity with appropriate adjectives, like I think the singularity has to be Gorenstein, it has to satisfy the hard Lefschetz condition. But anyways, then there's this thing called the Bryan-Steinberg stability condition, where you're also counting certain two-term complexes, where there's a somewhat relaxed purity condition. And so you can equally well form some notion of the so-called Bryan-Steinberg vertex of some threefold singularity. And you can ask, what is the wall crossing from PT to Bryan-Steinberg? And again, there's some very simple expected formula for this, which looks exactly like the DT-PT formula. And I think the exact same techniques ought to prove wall crossings like this as well. Wall crossings like PT to Bryan-Steinberg are interesting because it has to do with the crepant resolution conjecture. In some sense, the formula that's on the screen right now is 1/2 of the DT crepant resolution conjecture.
In the Bryan-Steinberg, here, what is the group G?
Sorry, what is what? Say again.
What is the group G?
What is the group G? G can be anything such that the singularity satisfies something called the hard Lefschetz condition. So you can imagine G is a finite subgroup of the
Can be even GL3, for example.
I think it has to be a finite subgroup of something like SU3 or SO3.
Okay, thank you.
Yeah. Okay. And so finally, as a slightly more ambitious goal, I think that so in the process of our wall crossing, we used a very tiny sliver of Joyce's universal wall crossing machinery. I think it's possible to use more of it, in particular for the full power of his universal wall crossing machinery. There will be some vertex algebra which plays a role, and I believe that we can construct some symmetrized version of this Joyce vertex algebra in the presence of a symmetric obstruction theory. And I believe that this symmetrized vertex algebra has to do with controlling what happens under the DT-PT correspondence to non-trivial descendant insertions, right? So for the theorem that we proved something about the integral of, in some sense, 1, right? But in principle, you can integrate any sort of descendant insertion. You can insert all kinds of tautological classes, and you can ask what happens when you do some insertion on the PT side. What does it change into on the PT side? This is called the DT-PT descendant transformation problem. And I think this the formulas for such transformations should be controlled by some Joyce-style vertex algebra. And that should be very productive future work. Okay, I'm so sorry for being 10 minutes over time. Thank you all for your extended attention.
Yeah, thank you very much. Questions? Yeah, okay. I have sort of a comment probably, because I don't think, I mean, of course, if you know well this Joyce wall crossing story, then you want to apply it to everything. But I believe that in this kind of questions, there are other approaches which can be useful. In particular, I mean, you develop quite sophisticated technique to prove that one thing is a product of two other things. Yeah?
Yes, that's right.
So which looks as a fact of representation theory, like, okay, good. And for that, there is this technique of, in your case, it will be a K-theoretical whole algebra, but
yes,
at the cohomological level, it's cohomological whole algebra.
That's right.
Maxim and myself. And there is a paper which I wrote a few years ago, I don't remember, 3, maybe, with Rabchak, Yang, and Zhao, about the cohomological whole algebras and perverse coherent systems on toric column. I mean, okay, good. So then kind of the upshot is that the cohomological whole algebra of your toric threefold acts on the cohomology of the moduli space of perverse coherent systems. Simplest case, it's Nakajima Nagao, but actually it can be any perverse coherent system. And so, of course, it acts on various versions. So when you take, so we also have some wall crossing in this chamber in perverse coherent shifts chamber. And I believe that this is the right algebra which can be used to prove results about equality of various characters. Moreover, we had another paper in the same team. It's not on perverse coherent systems, but on Nekrasov instantons, where we proved that there is a vertex algebra. Certain, it's not Joyce. It's far. Joyce is infinitely far from the right vertex algebra. It's Gayota and Rabchak vertex algebra at the corner, and this is the basic vertex algebra which correspond to C cube. All right. Then you use this partition, whatever this old stuff with partitions going to infinity. You just look at the toric diagram for your Calabi-Yau threefold, and you fill it with 3D partitions, which are infinite in some directions, but if you have a compact leg, they are finite. All right. So anyway, it's more kind of, it's not McMahon, of course, it's kind of more general. It's not topological vertex, it's gluing of such things. All right, but then there is some vertex algebra which acts on cohomology of the relevant moduli spaces, or in equivariant version moduli stacks. Yeah, I believe that, I mean, it might be, let me say it kind of, it might be interesting to look at this technique as well, because Joyce technique, it tends to be more and more complicated when you when your problem is geometrically more and more complicated. And this stuff, it's kind of, it's in a sense, it's more fundamental. because if you have a toric, you see, if you have a toric Calabi-Yau threefold, then DB Koch was, it has nice quiver. It has a presentation in the by quiver with a potential. So you have an underlying linear algebra, and so essentially cohomology or maybe K-theory. I haven't thought about K-theory, but many other people did. At least cohomology admits very explicit answer in terms of, it's called pyramid partitions. Probably you know all that stuff better than I do. Yeah, and so then this means that you have an explicit basis associated with the fixed locus in the cohomology, and you have explicitly written raising and lowering operators. So you can write down explicitly this representation theory, and so then maybe you do not have to go through the painful wall crossing for each chamber and kind of to replace by more qualitative arguments. So I just
So maybe I can say this. So I completely agree that actually the morally more fundamental way to prove something like the DT-PT vertex correspondence should be that you start from the vertex and you find some way using quantum algebra techniques, using Koha, using Keha or something, to characterize what is the vertex. Like maybe you write down some Q difference equation that it satisfies, or maybe you say that it's some element which is acted on by some vertex algebra in some specific way, right? And I believe that if you take these equivariant vertices, which I wrote down, and you specialize them so that they're non-equivariant, so that they're really just like, you know, like certain generating series of non-equivariant Euler characteristics. In that case, you can express them maybe as some trace of some operator, and the operator might be written in terms of some Koha, in terms of some Keha, in terms of some quantum group, whatever, in terms of raising lowering operators. And I think that's a very productive way to study the DT-PT correspondence, and also a lot of related things. And in particular, I wouldn't be surprised if already the technology for proving some kind of numerical DT-PT correspondence using that kind of approach, I wouldn't be surprised if that technology already exists.
Yeah, actually, if you go like sort of 1,000 years ago to the one of the initial papers of Akunkov, Nekrasov, actually it wasn't even MNOP. It was, I believe, two other guys were Rishitikhin and Wapa. Anyway, they presented the first an approach to deriving McMahon, and
that's
it was based on the vertex operators.
That's right.
Yeah, so
but the main difficulty which I want to emphasize is that once you include these equivariant weights from equivariant localization, like you really add back in the equivariants, it seems a little difficult to me to find some kind of representation theoretic characterization of these vertices.
But we worked with equivariant version of Koha with Rabchak, Yang, and Zhao. Everything was equivariant.
Yes, there's an equivariant Koha, there's an equivariant Keha, there's an equivariant version of a lot of these quantum algebras, but it becomes a little harder to characterize what is the equivariant vertex in terms of these algebras. If you work non-equivariantly, maybe you can say, okay, it's some trace of some operator, but it's, as far as I know, it's unknown what is the meaning of the equivariant vertex in terms of these equivariant algebras. There's some speculation that it should be some QQ character associated to some simple representation.
Yeah, but I believe, well, I don't know because I haven't thought deeply, but in our proof of this generalized AGT conjecture, we, after all this Nekrasov instantons, it's where these QQ characters arise. So we worked with cohomology, but maybe if we worked with K-theory, we would have, because, you know, for cohomology, we do not have quantum algebras, or toroidal algebras, we have Youngians, shifted
Yeah, that's right.
Youngians.
That's right.
Yeah, but maybe, I don't know, but we worked equivariantly, and I thought that what we did, it's equivariant vertex in cohomological sense.
Okay, okay, okay.
And there is a gluing procedure. That's what we didn't do. I wanted to give it to one of my students to glue. There was an algebraic paper without geometry by Prochaska and Rabchak, how to glue vertex algebras. So, which means that you can glue it from the vertex to an arbitrary toric diagram. Yeah. Okay. Yeah. Maybe I do not see something. Yeah, that's possible.
Yeah, it's possible that I'm also not very up to date on all of the very exciting current work that's been happening on this. But the other thing which I wanted to say is that actually the original goal of this project was not specifically to prove the DT-PT correspondence. It was actually to try to understand how this Joyce-style universal wall crossing works for symmetrized obstruction theories on Calabi-Yau threefolds. And actually, the application to DT-PT was one of the simplest things that could actually be made to work.
Dominic should be happy that you devoted sort of your life to to further extending his wall crossing formula, but in physics, as far as I can say, it's better to use our wall crossing formula. It's more effective, but I don't know. Since you already spent so much time on trying to understand how it works, maybe you should continue. Yeah, all right.
There certainly are various aspects that actually become simpler in the presence of some symmetric obstruction theory. I think a lot of the combinatorial complexity that happens in Joyce's original work is because he has no assumption on what the obstruction theory looks like. It's some arbitrary thing. And when you have some arbitrary thing, I mean, when you run all these master space arguments, you can't control what the residues are, and you end up with some horrible combinatorics. But I do believe that if you try to run the same story with some symmetric obstruction theory, maybe for something which looks 3 Calabi-Yau, then I think you should get simpler formulas, actually, not more complicated ones. So that's the hope.
Okay. Okay, more questions?
Actually, I was going to ask about Yan also already asked it. So given this PT DT product formula conjecture, and which to me was a representation theorist that looks like a var character formula. The PT looks like a character of a Verma module, and the D. Oh no, PT is the character of irreducible module, and of giving the highest weight, and the P. Let me see, the larger one is the DT. That is the Verma module. So now, from what Yan was talking about in terms of cohomological whole algebra, or and basically you don't have this kind of a theoretical structure, whether you take spherical whole subalgebra, you do a Greenfield double to get something looks like a entire whole quantum group. So did you, I'm sure that you have discussed this with Nakajima. Also,
not yet, actually. I've already been here.
I'm sure he mention that you could formulate this in somehow that found some sort of a representation that this DT character, it's a character, but this time it's not over complex numbers, but the field is going to be with multiplicities in something much more complicated.
Okay. I guess in that sort of direction, I can say the following thing, which is that if you forget about these equivariant weights, small w superscript k here, and you really just have a numerical generating function, then I completely agree with what you said. In fact, I can be even more precise. The DT and PT, K-theory groups of the DT and PT moduli spaces, they're actually very explicit things. You can identify them by what the fixed points look like. And actually they look like Verma modules for something called the shifted quantum affine, shifted quantum toroidal GL1 algebra.
Quantum toroidal, okay.
Quantum toroidal, yeah. So the K group of the usual Hilbert scheme of points on C2, that's the Fock representation of the unshifted quantum toroidal GL1 algebra. And what happens when you go one dimension higher to these DT and PT, these three-dimensional configurations, is you can show something roughly like these things are something like Vermas for shifted quantum toroidal GL1.
Mm-hmm.
And the shift for PT and the shift for DT are slightly different. Okay. And so then you can ask, okay, how to compare these Verma modules? And the answer is I think there's some kind of induction procedure where you change a representation for one shift into a representation for another shift. Mm-hmm. And then there's some way to compare their characters. But in this kind of approach, when you say the word character, you really just mean a sum without this weighting, this rational function WK. It's really just a numerical sum, right? It's a sum of.
I mean, classically, the characters are, you're really doing the dimensions, but if you do have, for example, another C-star action, and the C-star preserves each weight space, that gives you another parameter.
Right.
Instead of numbers, but you can get a formal series of that numerical parameters.
Right, that's right. So the main challenge, at least for me, in this kind of approach, is to ask what is the representation theoretic meaning of these rational functions WK.
Yeah.
These things arise from equivariant localization in terms of geometry. They have to do with something like the virtual normal bundle. And it's kind of unclear to me, like, what is the representation theoretic operation you should do such that you get this weighted generating series as opposed to just the numerical generating series. Yeah.
Okay, thank you.
Any more questions? Well, if there are no more questions, so thank you very much. So let's thank the speaker. Very interesting talk.
Thank you all for your attention.
Thank you. And for you, have a good day because your day is just started.
Yes.
Yeah.
That's right.
And for us, well, that's the end of the seminar.
Nice.